So, first of all, let me thank all the grad students who have been worked through the years in my group. Here are the pictures of them and the dates that they got their PhD, except for Manali, who is in this meeting, but he transferred to University of Utrecht, to a better place, and got his PhD there. So all the good stuff comes from them, and anything that's bad, I'll take responsibility for. The other thing is, of course, I need to thank the National Science Foundation for all the funding they gave me over the years, and the University of Nebraska-Lincoln. All right, so we all know this picture, double slit and the de Broglie-Bohm pattern. And of course, one question is always, come and say more about the physical nature of the guiding field. One thing I came across some years ago is this lovely book from Luis de la Peña, Emilio Zetto, and Andrea Hernandez. And deeper in the book, you find this picture of a double slit. So here at the top are the two double slits and their trajectories calculated. They actually jump, if you would zoom in this area, it looks very much like the Broglie-Bohm. And this piqued my interest because, of course, here they have a specific physical mechanism. It's the electromagnetic vacuum field that is acting somehow as the guiding field for this. So the idea is something like this. You have a double slit, you see some kind of vacuum field boundary condition, the electron is guided and gives rise to diffraction according to this idea. So I communicated with the person who was responsible for the simulation, Jaime Avendaño, and he has a model, and we checked the analytics, which as far as I know is correct. Electron clock couples to the Compton frequency vacuum field. So you have a Compton frequency shaking charged particle that is interacting classically with electromagnetic field. You assume that the velocity is such that there is no Lorentz force. This is the basic assumption of the entire thing. And then you arrive after some couple of pages of analytics as this particular guiding equation where V is the velocity of the electron and E is the E field of the vacuum field. Now, to give this any meaning, we have sadly to do something that is funny. We have to change the Compton frequency to the de Broglie frequency here, otherwise nothing works. So why that is, I have no idea. But if you do so, then you get this result for simulation. So we have Avendaño's code and we ran it for all kinds of different situations. And it does represent these equations. The quantum mechanics gives the orange results and the clock model gives the blue results, which gives us very nice agreement. And then you say, all right, that's kind of something that is a big surprise, to me at least, when I got my hands on this. And of course, you can compare that then to the Broglie-Bohm velocity, where this equation we can compare to this equation, and it's of course very similar in structure. This gradient brings out an imaginary number, so this is a real equation, or you could just take the imaginary part of the, drop the I, and it looks even more like this.
Herman, sorry, quick question. I think a number of us might be confused. What do you mean by the de Broglie frequency?
Oh,
wavelength, but the de Broglie frequency.
Well, if you have a lambda dB and you have a velocity, then you can divide the two by each other, and then you have and the inverse of that would then be the de Broglie frequency.
So the de Broglie length and the particle velocity? Okay.
Yeah, that's always a big deal, of course, right? What are you using, the Compton or the de Broglie? And anyway, so since I come from an experimental groups and mostly in the past, and now also in matter optics, we usually take the Schrödinger equation, take care of the time-dependent part, you get an Helmholtz equation, and in free space, you can show that this, of course, follows from that. Now, of course, we know that for electric fields, you can get a similar Helmholtz equation, and thus it's not surprised that you would get that type of solution too, right? And then, you can then find the right for constant, which indeed goes into model. So it's kind of amusing if, of course, you take the same wavelength for matter waves and you take the same wavelength for an electric field, then since these waves couple, if you just find the right Fourier constant, you of course map on the Broglie-Bohm system. I find that, yeah, an amusing, interesting observation, except this came from a fundamental derivation that Jaime did based on a totally different assumption that the Lorentz force average is 0. Yes? Okay. So what are the numbers? The numbers are, since we've of course done the double slit experiment, I won't go into that. We made a nanofabricated, slits, 300 nanometer separation, and you get stuff, and then you can put 500 eV electron beam in. You can range the energy this way if you like, and then you could compare that with what we do in the simulation, and that's what we did. Here is an experiment. This was done by Roger Bach. Here is closing the nano slits one at a time, and you can also record this one particle at a time, and that was well received, and it is all due to this wonderful person. But for these X-rays, it's supposed now the vacuum field that the wavelength matches the Broglie wavelength of the electron, which happens to be vacuum X-rays. Now, vacuum X-rays, if you take one of these nanometer thin things, X-rays just penetrate like crazy. And here's the transmission for lead, where you have a thickness of centimeters. So you might say, gee, can vacuum X-rays diffract at all? I mean, I decided to look into that. So we have a vacuum diffraction machine that happens to have fantastic forward resolution. And so with the D8 Discovery, we did that. I just took, of course, real X-rays and not vacuum X-rays, because they would be hard to detect. You put a nanofabricated grating in, but this close to the same period as the double slit. Grating gives you more signal. Didn't do it for the double slit, but same thing. And see, can we actually measure that diffraction pattern? The answer, and then the motivation for this was a quote from the book, The Emerging Quantum, from De La Peña and Seto and Hernandez. The electrons maintain their corpuscular identity all along the experiment. There's no need for particle self-interference. Since the diffracted field exists even in the absence of the electrons, that means that vacuum field diffraction, it might be possible to put this explanation to experimental test. The observation of the diffracted field with independence from the present or absent electrons would demonstrate that it's the field, not matter, which is diffracted. That's interesting statement. That was one of the motivations to look at this. So anyway, we switched from electrons of 1.5 angstrom to X-rays, and here is the data. As you can anticipate, most of it goes through. So you have a central peak. Here we scan left to right. You do see the little side order, and here the little side order. It's really, really small. If you look at a log scale, you can see that these side orders sit in the right location, but are suppressed by about 5 orders of magnitude. But they're there. So there is a big part of that field goes through. There's nothing. And there's a small part, about 1 in 10 to the 5th, that is diffracted. So the diffracted field is actually there. So that's kind of nice. And of course, you would expect for a vacuum field that it would be diffracted too, right? Not just this real field. So indeed, one might worry that that there's some kind of, messing up of the quality of the diffractive field. Well, yeah, the quality I would like to get better, but it's already pretty hard to measure to 1 part in 10 to the 5th or 1 in 10 to the 4th or something like that. So I can't do much better than seeing these side lobes for this particular experiment. But it's nice. And of course, as soon as you have that, then you might also say, how come that this is not material dependent if you have more diffraction? Well, keep in mind the guiding equation depended here on the gradient of E over E. So somehow the amplitude of the field drops out of the guiding equation. So as long as you have the spatial pattern, you would get this guiding equation. It's all somewhat mysterious to me, but it seems possible. Again, that's of course the electron diffraction pattern from the same nanofabricated grain that we took, including with the Schrödinger solution. And I'm not going to talk about this. All right, so we may have another way to go at this. This was an interferometer with 3 nanofabricated gratings that we once built, and and I'm not playing with the idea of seeing the recoil. When we tune this interferometer so all the electrons come out in one arm, there should be a recoil, but the recoil should be first transferred to the field. So if we actually start measuring the recoil on a nanofabricated grating or a little piece of it, then maybe that gives an idea to actually see the effect in the vacuum field instead of real X-rays. So that's an idea I'm toying with right now. All right, so another thing is if we go back to the simulation, one question is which modes of the vacuum field cause diffraction? This was with 10 modes, and then you get pretty darn good agreement. But if you drop the relevant modes, so the modes extend through all space, so if here's a double slit, but the boundary conditions in this direction, here I throw 3 modes, tell you, put a limit on all the modes you can use. Here's 3 modes, here's 1 mode. So even 1 mode, the red mode, is sufficient to explain the peaks. And that's interesting because that would tell you that, okay, indeed, you already should, it should be sufficient in the vacuum field to just consider that 1 mode where its wavelength matches the electron de Broglie wavelength. And that's what this model indeed tells you. So it's not a collection of all modes, but 1 mode, according to this model. Of course, there's lots of problems with the model. Why did we change the Compton frequency, the Broglie frequency? The Lorentz force is not 0 in all scenarios because this is an assumption, so that's not justified in the other way. There's some other ones. So is this use of the boundary condition justified when the wave penetrates so strongly? Well, after all, our first measurement of the diffracted field seems to now indicate that at least is yes. So this is kind of a nice thing that we do when we have free time in the evening. This is what we work on a little bit. Really fun. For this meeting, I really had no idea what to talk about, so I decided to throw in some other experimental works that we're working on in matter optics. One is this, and since John, you mentioned Barry's thing, we had a result 2 years ago with the group of Jo Verbeek in Belgium. And we took an electron beam, here the blue beam, pass it by a solenoid, an aperture, and we look at the pattern. This is the usual Arnold-Bohm experimental configuration. What we saw, here's the observation. So we scan here along the direction, and we see, depending on how strong the current is in the solenoid or the magnetization of the material, we see that we get an asymmetric pattern. So an average deflection to the right or the left. This was the predictive Cherenkov-Berry quantum force. There was a little riddle because Peskin and Zeilinger predicted that in the Arnold-Bohm situation there was no force predicted, while Cherenkov and Berry predicted there was a force associated with the Arnold-Bohm system. And we confirmed that that force is there. Earlier, how do you know, by the way, if there's no force? Well, you know, you just look at a deflection of a beam or a delay of the beam, right? That's what you do, it's operational. So measure force, this is what we did already in 2007. We shot an electron on a femtosecond needle, generated in a little burst, and then we timed when it arrives. And then we ruled out, so this is part of the experiment, we ruled out that there's no forward force that could explain the Arnold-Bohm effect, and that was at that time appeared well on the cover of Today, together with Tonomura, which was a lot of fun. So we showed that there was no force. There's an effect, but no force. That's what it's famous for. That was the regular AB phenomenon on the left, the Peskin-Zeilinger. So we confirmed this theory. Then you had Cherenkov-Berry, and we confirmed that there is a quantum force. And so then the question began, how can you reconcile the theory? And we did that too, or actually Maria Becker did that, who's now a professor at, she's moved to Nebraska-Lincoln University. And she figured out, I'm not going to go over this, but how you can get from quantum mechanics in 2 limits, either what is called the Zeilinger dispersivity theorem that tells you there's no force, and the Cherenkov-Berry quantum force, which pretty much this is the longitudinal and the transverse direction. That's what it comes down to. And so we've also reconciliated the thing. Why I'm showing this is because I thought that, you know, for people who do bouncing oil droplets or do the Broglie-Bohm calculations, it might be fun to take this Arnold-Bohm system and hunt for the Cherenkov quantum force, because there is a deflection. It is not just the usual Arnold-Bohm phase shift. I thought that might be fun to show, and there's experimental evidence now since 2 years for that. So yeah, and this was published. Here's the reference for 2019. All right, since I work in what I would like to call an area that we're trying to open up with a couple of people is free electron quantum optics, and here's some of these topics we worked on. Kapitz-Dirac was mentioned before. I just mentioned the Arnav Bohm and the new quantum force and the double slit, blah blah blah. Yeah, here's one of the newer ones, which is changing a harmonic oscillator in a two-level system, which was just published. What are we doing now? We're doing now, maybe this is maybe fun. If you take a wave function in free space, so say there's a Gaussian wave packet. Suppose you try to put one electron in there with spin up. Then no problem, you could do that. Try to put two in, and it says, no, you can't do that because, of course, Pauli exclusion principle is at work. But suppose I try to do it so fast that the speed of light cannot signal its presence. So that this is bigger than c delta t. Will you then still block the presence of that second electron?
Oh, yes.
Okay, that was an answer. Is the Pauli exclusion principle non-local or not? So I would say that if it's a symmetry principle, you would say you block it. If anybody would like to come up with a local explanation, then maybe perhaps not. And it's one of my dreams to experimentally maybe demonstrate the non-locality of Pauli exclusion principle. Might also be interested in the context of non-locality that we've been talking about. Is it experimentally hard? Yeah, sure. I can make wave function blobs for electrons of about a micron. And that means that with the speed of light covers this distance in about 10 to the minus 14 seconds. Well, that's okay because the laser pulses that we have are about 100 femtosecond, 50 femtoseconds, and the electron pulses we make are about 10 femtoseconds. It's on about time. So when we have a metal tungsten tip, we hit it with a femtosecond beam. The front of this we can make about a micron. Usually they're a little sharper, like 100 nanometer, but we can make them a little bit bigger and still get electrons. The time is of that nature. And then what you do is you try to select pulses where two electrons come out, and with a coincident circuit try to see if you can see these two electrons. Well, we very recently succeeded in seeing two electrons talk to each other in this way, in this time scale and length scale. So here is these peaks as a function of time. So it is something like this. This peak means one laser pulse makes an electron, and the next laser pulse is a pulse laser makes the next electron. Then you land up here. If one electron is born and then the next laser pulse does nothing, and the second to next does something, you land here. However, if both electrons are made by the same laser pulse, you end up here. And this dip, so you have all the same height, and this dip is an indication of the interaction between the two electrons. So we have a very strong phenomenon there. And of course, then the question is that due to the Coulomb force pushing these electrons out of the detector, or is it the fact that Pauli exclusion principles stop these electrons from being together? I would like this, but for this particular parameters, I knew that this phenomenon is really due to Coulomb interaction. So the red line is the simulation. It lies very nicely on the black data points. The blue line is without interaction. So indeed, we can at least see this interaction now, and we have rebuilt the machine so we can reach the new parameter space where this tip is larger, and thus the Coulomb interaction has been suppressed. And we're trying to take data as we speak to see if we can see the Pauli blockade. And of course, then also, we are already automatically in the regime where we might be testing the locality or non-locality of Pauli exclusion principle, which is one of my dreams. So, and of course, how you find out if it's due to Coulomb or Pauli other than changing the size? Well, we've in the meantime developed a fast spin polarized source, femtosecond nanoscale. We have a US patent on that, and it's published in Applied Physics in 2019. So if this becomes gallium arsenide and we pump with circular polarized light, you can get polarized electrons. And then we can, since Coulomb is not dependent on polarization of the electron, but Pauli is dependent on polarization, you could determine how much is due to one or the other. The dip by itself is submitted to PRL. We'll see if the reviewers treat us nicely or not. And the work is done by Sam Karamati, who sadly had just got another job, so he is going to leave, and that's for me bad, for him great. How much time have I got? John, how am I doing?
You're doing fine, 10 minutes.
Oh, great. So I'm rushing through 116 PowerPoints. Sorry about that, guys. Just perk some ideas up and see if there's something to your liking. Decoherence theory. So there was an idea by Wojciech Zurek that if you take an electron, you make an interferometer, you send it over a surface, and the electron sets an image charge. This image charge rattles around, that gives a back action electron and eats the coherence of the interfering thing. We realized that system with an electron gun, a grating, and we bring a surface close, and we try to see that. Part of that is first published in 2018. Also following actually the work of Professor Hasselbach in Tübingen, Germany. So that's fine. We tried to make the effect larger. We published this in EPL. So this is without a surface, and this is with a surface. So this is the diffraction pattern recorded here from the grating. It's nice, resolved multiple orders. This is when you put this grating close, and this is close to the grating. This is further away from the grating, and say, oh, that's good. The contrast goes away. We're seeing the transition from quantum to classical dynamics. Sadly, this is not true. What it is some electrons skirt the surface. They cause secondary emission, and you get patches of charges. These patches of charges make a random potential that dephases instead of decoherence. Decoherence is a time irreversible process, dephasing time reversible. There's a fundamental difference. So that is understood. The model, we can model this. Here's the experiment. Here's the simulation of the pattern. So we think we fully understand this. And as with all experiments, you first have to rule out all the crud effects before you can go to the stuff that you really want to see, which in this case, making this controlled decoherent environment. I thought I was smart at some point and said, okay, you know, you take gallium arsenide, you put light on it so you can change the conductivity, because the image charge in this stuff that causes decoherence is controlled by how conductive is the surface. Gallium arsenide without light is non-conductive, with light is conductive, and it changes by orders of magnitude within the parameter range of the theory that Zurek proposed. Here's the data for that. And then this is the position of the surface, and this is what the electron does. So, and here is where the laser hits. This is when you can excite the band gap when it's supposed to be conductive, and you get a huge deflection. Then you go with a laser that is not capable of exciting the band gap, and you still have a huge deflection, but the other way, which was a mystery to us at first. So we contacted people that were experts in condensed matter, and I had to learn a lot about condensed matter physics, which was painful. So, you know, we did the simulation. We figured out there's what is it called, trap state and surface states, and there a donor migration and whatever. There's all kinds of phenomena in the rate model, but we figured it out, so we understand this. So there is another phenomenon going on. It does actually tell us, we just submitted this paper too, that let me actually go to this slide. We pushed it to the limit where we have a golden channel where the electrons go through. And even if this bounces multiple times, so we approach this very closely and the decoherence is by model very large, we still see a diffraction pattern coming out. And this has the same contrast as the original beam in this picture, which was a huge surprise to me. So the deal is we're either going to say that all the models that are out there, about 4 theoretical models, are just wrong in predicting decoherence for electron diffraction. And then, or our experiment somehow fails. But if the decoherence is much less, that is great, because then we can make a coherent fiber for electron waves. Because then we can just take that gap with multiple gaps behind each other and making a technology that is actually worthwhile. This work was done by Zilan Chen, who also is hired away. So I've lost him 3 weeks ago, sadly. Also got the PhD and nice. But yeah, so on the one hand, I'm excited about it because we can get this technology. But on the other hand, this is not really fundamental, except for the fact that the decoherence is so weak. one of the other motivations that I wanted decoherence is because this thing that I found in Stanford, that is in the Broglie-Bohm theory. Let me read it. In case of decoherence, you got stuff. And what it would happen that decoherence would arguably resolve the puzzle discussed in Holland, where he discussed the classical limit of the Broglie's theory. One baffling problem, for instance, is that trajectories with different instruments cannot cross into the Broglie-Bohm theory. We all know that, right? But but as soon as you get decoherence, then in Newton's theory, they do cross. Now, decoherence can allow these trajectories to cross. So I thought, oh, it would be lovely to have a system where you have decoherence. So if you can get a system that acts like a de Broglie-Bohm type system, a guided wave, and if you can get a system where you have the particles non-crossing, then the only thing you need to do is introduce noise. So to show that then you start, number one, losing your contrast, but at the same time get crossing trajectories. So there's nothing wrong with the limit of going from a guiding equation, but then a guiding equation with decoherence, you can reach Newton's equation. And I thought that was maybe the tie into this meeting, so that that physical system, which we are trying to realize now with electron wall system, is also from that point of view potentially interesting. Okay, good. All right. Yes, and I haven't seen that yet. Oh yeah, and I wanted to make this comment. There was this paper in Quantum magazine, which famous experiment dooms alternative to quantum weirdness. So this is the oil droplet stuff. And somewhere in this person who wrote this for Quantum magazine also interviewed me. My name is used or abused here, one or the other. So they say that we also invalidated Coudé's experiment. I do not think that we invalidated that. I think that, I think it should be pretty self-evident that you can get interference-like pattern by classical particles, by classical waves, which most of the community here, in this community, people believe. So the way that this article was written, I do not subscribe to. I wanted to end with that thought. Thank you for your attention.